Hello there, and welcome to the Sleepless Era channel. I'm so glad you're here. Tonight's journey is a long one, 4.5 billion years to be exact. But there's no rush, nothing to memorize, nowhere to be. Just the story of this planet, unfolding slowly, the way it was always meant to. Let your breathing slow, let your thoughts drift, because we're traveling through deep time tonight. From a spinning cloud of dust, to molten oceans, to the first breath of life. Through ice ages and eruptions, forests and deserts, and creatures so enormous they shaped the land itself. Some nights, the biggest stories help us rest. They remind us how ancient this ground is, and how small our worries become in the vastness of it all. If this quiet journey brings you peace, consider subscribing. It helps others find their way here too. Now, let's begin.
Before there was Earth, there was only dust and darkness. A cloud of gas and debris drifting through space, silent, invisible, stretching across trillions of miles. It had no name, no shape, no purpose. Just particles suspended in the void, leftovers from stars that had already lived and died. This cloud, what we now call the solar nebula, had been drifting for who knows how long, maybe millions of years, maybe longer. Time had no meaning yet. There was no sun to mark the days, no planet to circle it. But then, something happened. A nearby star exploded, a supernova. The shockwave rippled outward, invisible but unstoppable, and when it reached our quiet cloud, everything changed. The cloud began to collapse, not all at once, not violently, just a gentle inward pull as gravity took hold. Particles that had been drifting apart for eons now began to fall toward the center, slowly at first, then faster. As the cloud collapsed, it began to spin. Like a figure skater pulling in their arms, the rotation accelerated. The cloud flattened into a disk, swirling around a growing center of mass. And in that center, something was forming. The proto-sun. Not yet a star, not yet burning, just a dense, glowing sphere of gas growing heavier with every particle that fell into it. The pressure built, the temperature rose. The center began to glow red, then orange, then white. Around it, the disk continued to turn. Dust and gas spiraled inward, but not all of it reached the center. Some of it stayed in orbit, circling the newborn sun. And within that disk, small clumps began to form. Grains of dust collided. They stuck together. Electrostatic forces held them in place. Grain by grain, they grew. These clumps became pebbles. Pebbles became boulders. Boulders became planetesimals, small bodies only a few miles across, tumbling through the disk.
And one of those planetesimals, still unnamed, still unformed, would eventually become Earth. But that would take time, millions of years. For now, there was only the disk, the proto-sun, and the slow, patient process of gravity pulling matter together. The solar system had begun, quietly, without ceremony, just dust collapsing into something new.
50 million years passed. In cosmic terms, barely a moment. But for the growing Earth, it was enough time for everything to change. The planetesimals continued their work, colliding, merging, building mass. Each impact released energy. Kinetic energy converted to heat. And with every collision, Earth grew hotter. The surface was not solid. It could not be. The constant bombardment, the compression from gravity, the radioactive decay deep within, all of it generated heat faster than it could escape. Earth became molten. Not partially, not in places. The entire outer layer of the planet was liquid rock, a magma ocean, glowing red and orange, stretching across the entire surface.
The temperature reached over 1,000 degrees Celsius. In some places, perhaps as high as 1,600. There was no ground to stand on, no continents, no oceans, just molten silicate, churning and convecting as heat from below pushed upward and cooler materials sank back down. The atmosphere, if it could be called that, was thick and toxic. Water vapor, methane, ammonia. Gases that had been locked inside the planetesimals were now released, escaping from the magma as it churned. The sky would have glowed, not with sunlight, but with the heat radiating from the surface itself. A hellish orange haze, thick with vaporized rock and steam. And yet, even in this chaos, something remarkable was happening. The heavier elements were sinking. Iron and nickel, denser than the surrounding silicate, began to fall toward the center. Slowly at first, then in great waves as the planet differentiated itself. This process, called planetary differentiation, was not gentle. As iron sank, it released even more heat. Gravitational potential energy became thermal energy. The planet grew hotter still. But this sinking iron was forming something essential. Deep below the molten surface, a core was taking shape. A metallic heart that would one day generate Earth's magnetic field, shielding the surface from solar radiation.
For now, though, Earth was simply hot, unrecognizable. A glowing sphere of liquid rock spinning in the darkness, waiting for the next great collision that would change it forever. The Hadean Eon had begun, named after Hades, the Greek underworld. And for good reason. This was Earth at its most violent, its most unstable, a world that would have been utterly inhospitable to anything resembling life. But it would not stay this way forever.
Earth was not alone in its orbit. Another body had formed nearby, a planet roughly the size of Mars, spinning through the same region of the solar system, following a similar path around the young sun. Scientists would later name it Theia, after the Greek Titan who was the mother of Selene, the goddess of the moon. For a while, perhaps millions of years, the two planets coexisted, Earth and Theia, orbiting the sun, their paths occasionally crossing, but never quite meeting. But orbits are not permanent. They shift, they wobble, and eventually, gravitational interactions pulled Theia off course. It began to drift toward Earth, slowly at first, then faster, until there was no avoiding it.
The collision happened about 50 million years after the solar system formed. In geological terms, Earth was still an infant. Theia struck at an angle, not head-on, but at roughly 45 degrees. The impact was not instantaneous. It took hours. The energy released was beyond comprehension. Both planets melted. The outer layers vaporized instantly. Rock turned to gas. The atmosphere, if it had begun to form, was blown away. Massive chunks of both Earth and Theia were flung into space. Molten rock, vaporized silicate, and iron-rich fragments scattered into orbit around what remained of Earth. For a moment, there was chaos. A ring of debris, glowing red-hot, circling a wounded planet. But gravity does not rest. The debris began to coalesce. Particles collided, stuck together, and grew. Larger fragments attracted smaller ones. Within the debris disk, clumps began to form. And then, remarkably quickly, the moon took shape. Some simulations suggest it formed in as little as 40 years. Others propose it took thousands, perhaps tens of thousands of years. Either way, in cosmic terms, it was nearly instantaneous. The moon that formed was much closer to Earth than it is now, only about 15,000 miles away compared to the 250,000 miles it sits at today. It would have filled the sky, enormous, glowing, a constant looming presence overhead. The tides it created were immense, 100-foot waves crashing onto the molten surface of Earth every few hours as the moon's gravity pulled at the liquid rock. But over time, the moon drifted away. Tidal interactions transferred angular momentum from Earth to the moon, slowly pushing it outward, inch by inch, century by century. And deep within Earth, something remained. Fragments of Theia, denser than the surrounding mantle, sank and settled near the core. They are still there today, buried over 1,000 miles below the surface. Two massive blobs, each roughly twice the mass of the moon itself, remnants of the planet that gave birth to our satellite. The collision changed everything. It tilted Earth's axis, giving the planet seasons. It stabilized its rotation, and it gave Earth a companion, a moon that would one day influence the tides, light the night, and become a beacon for the life that had yet to emerge. For now, though, Earth was still molten, still violent, still waiting to cool. The moon hung in the sky, massive and watchful. Earth spun below, still glowing, still molten. But something was beginning to change. The bombardment from space was slowing, not stopping entirely. Asteroids and comets still crashed into the surface, but less frequently now. With each passing million years, the impacts grew more rare, and with fewer collisions came less heat. The surface began to cool. Not all at once, the magma ocean didn't freeze solid overnight, but slowly, over millions of years, a thin crust began to form. Patches of solid rock floating on the molten layer below.
These patches were unstable. They cracked. They buckled. They sank back into the magma and reformed elsewhere. But gradually, they grew larger, thicker, more permanent. By about 4.4 billion years ago, Earth may have had its first solid crust. The temperature at the surface dropped from over 1,000 degrees to perhaps a few hundred degrees. And when the temperature fell below a critical threshold, something remarkable happened. Water vapor in the atmosphere began to condense. It started as rain, not gentle, not soft. These were torrential storms, lasting not hours, but centuries, perhaps millennia.
The water fell onto the cooling rock and immediately turned to steam, rising back into the atmosphere. But as the surface cooled further, the steam stayed water. Pools began to form, then lakes, then something larger. The first ocean was forming. Where did all this water come from? Some of it was already here, trapped in the minerals of the planetesimals that built Earth, but much of it arrived from space. Comets, icy bodies from the outer solar system, crashed into Earth during a period called the Late Heavy Bombardment. Each one delivered water, ice, locked away for billions of years, now melting onto the surface of a planet that desperately needed it. The early ocean was not blue. It was not clear. It was likely murky, filled with dissolved minerals, iron, and sulfur leached from the volcanic crust below. The sky above was still not the blue we know today. Without significant oxygen, The atmosphere was likely tinged with orange and red, thick with carbon dioxide and methane. But there was water, liquid water, covering perhaps most of the surface, broken only by scattered volcanic islands that rose and sank with the churning mantle below. Earth had its first ocean, and with water came possibility. The planet was no longer a hellscape. It was not yet hospitable, but it was becoming something else, something that could, one day, support life. For now, though, the ocean was empty, silent, waiting.
The Hadean Eon, named for the Greek underworld. A fitting name for a time we barely understand. No rocks survive from this period. None. Every rock, every grain of sand that existed on Earth's surface 4 billion years ago has been destroyed, recycled, melted, or buried so deep we may never find it. What we know about the Hadean comes from meteorites, moon rocks, and computer simulations. We piece together the story from fragments. The surface was still volcanic, not as violently as before, but active. Lava flowed from fissures in the thin crust, spilling into the ocean, creating new land, only to have it swallowed again.
The atmosphere was thick. Carbon dioxide, methane, ammonia. Greenhouse gases that trapped heat and kept the surface warm despite the young sun being dimmer than it is today. The ocean was acidic. Rain falling through the atmosphere picked up carbon dioxide, forming carbonic acid. It ate away at rocks, dissolving minerals, creating a soup of chemicals. And yet, this hostile world may have been more habitable than we once thought. Recent studies suggest that by 4 billion years ago, Earth may have had a moderate climate. Not hellish, not frozen, just temperate. Liquid water existed. Temperatures may have been no higher than a hot bath. The crust was thin, but stable enough to support land masses.
And in this environment, somewhere in the dark, wet corners of the planet, chemistry was happening. Organic molecules were forming, amino acids, the building blocks of proteins, nucleotides, the precursors to DNA. These molecules didn't form from nothing. They required energy, raw materials, and time. Lightning provided energy, volcanic vents provided heat and minerals, and time, well, time was abundant. No one knows exactly where life began, perhaps in a shallow tidal pool, warmed by the sun, perhaps near a hydrothermal vent on the ocean floor, where hot water rich in minerals bubbled up from the crust below. What we do know is that by the end of the Hadean, the stage was set. Earth had water, it had land, it had an atmosphere, and somewhere in that ocean, molecules were learning to replicate. Life had not yet arrived, but it was close.
The Archean Eon began 4 billion years ago, and somewhere within its first few 100 million years, life appeared. We don't know exactly when. We don't know exactly where, but we have evidence. The oldest rocks on Earth, found in Greenland and Western Australia, date back to around 3.8 billion years ago. And within those rocks, there are hints. Carbon isotopes, ratios that suggest biological activity. Something was processing carbon in a way that only living things do. The first life was not complex. It was not visible. It did not move or think or respond to its environment in any way we would recognize.
It was simple, single-celled, likely resembling modern bacteria, but even more basic. These organisms, if we can call them that, did not need oxygen. In fact, oxygen would have been toxic to them. They lived in a world without it. They may have been chemotrophs, organisms that derive energy from chemical reactions rather than sunlight. They may have clustered around hydrothermal vents, feeding on hydrogen sulfide and methane. Or they may have been photosynthetic, using sunlight to convert carbon dioxide and water into energy. But not the kind of photosynthesis we know today. This version didn't produce oxygen. It produced sulfur instead. Wherever they lived, whatever they were, these first organisms had one crucial ability. They could replicate.
By 3.5 billion years ago, life had found a new strategy: photosynthesis. But this time, a different kind. A kind that used water as a raw material and produced oxygen as waste. These organisms were cyanobacteria. Simple, single-celled, but revolutionary. They clustered together in shallow coastal waters, forming layered mats of bacterial slime. Over time, sediment settled on these mats, and the bacteria grew on top, creating new layers. Year after year, century after century, the layers built up. These structures are called stromatolites.
They could make copies of themselves. Not perfectly. Sometimes the copies had errors, mutations that changed their structure or function. And sometimes those changes made them better suited to survive. This was evolution. Not guided, not planned, just a process, unfolding according to the laws of chemistry and probability. For hundreds of millions of years, life remained simple. Single cells, drifting in the ocean, reproducing, mutating, competing for resources. There were no predators, no ecosystems, no food chains, just individual cells doing what they could to survive. But they were changing the planet. Slowly, imperceptibly, their metabolic processes were altering the chemistry of the ocean and atmosphere. They were setting the stage for something much larger. Life had arrived, quietly, without fanfare, and it would never leave.
They still exist today in a few rare places like Shark Bay in Australia, but billions of years ago, they were everywhere. Coastal waters around the world were filled with them, massive reefs of bacterial colonies, quietly pumping oxygen into the water. At first, the oxygen didn't accumulate. It reacted immediately with iron dissolved in the ocean, forming iron oxide, rust. This rust settled to the ocean floor in layers, creating formations we now call banded iron formations. These layers are visible today, stripes of red and black rock, evidence of an ocean rich in iron and an atmosphere slowly filling with oxygen.
For a billion years, the ocean absorbed the oxygen. But eventually, the iron ran out. There was nothing left to react with. And so the oxygen began to escape into the atmosphere. This was the Great Oxidation Event. Around 2.4 billion years ago, oxygen levels in the atmosphere began to rise. For most life on Earth at the time, this was catastrophic. Oxygen is reactive. It damages cells, breaks down organic molecules, and creates toxic byproducts. For organisms that had evolved in an oxygen-free world, the rising oxygen levels were poisonous.
Many species went extinct. This may have been Earth's first mass extinction, caused not by an asteroid or volcano, but by life itself. But some organisms adapted. They evolved mechanisms to tolerate oxygen and eventually to use it. Aerobic respiration, the process of using oxygen to extract energy from food, is far more efficient than anaerobic metabolism. Life that could breathe oxygen had a massive advantage. They could grow larger, move faster, and do more with the same resources. The stage was set for complexity. But that would take time, another billion years in fact. For now, the world was still dominated by single-celled organisms. The continents were barren, the oceans were murky, and the sky, for the first time in Earth's history, was beginning to turn blue. Beneath the ocean, something else was happening. The crust was moving, not quickly, not visibly, but constantly. Driven by heat from the mantle below, the tectonic plates that made up Earth's surface were shifting, colliding, pulling apart. The first continents were forming. Not the continents we know today. These were smaller, scattered land masses, volcanic islands that had grown large enough to resist being pulled back into the mantle.
They were made of granite, a rock lighter than the basalt that formed the ocean floor. This lighter rock floated on the denser mantle below, creating stable platforms that would become the cores of future continents. Geologists call these ancient cores cratons. They still exist today, buried beneath younger rock, the oldest parts of the continents. By 3 billion years ago, these cratons were beginning to merge. Plate tectonics, the process that drives continental drift, was fully operational. When two land masses collided, mountains formed. When they pulled apart, rifts opened, and magma rose to fill the gap.
The first supercontinent may have formed during this time. We call it Valbara, though the evidence is sparse and debated. If it existed, it would have been much smaller than the supercontinents that came later. Just a few cratons fused together, surrounded by a global ocean. But the important thing was that the process had begun. Continents were drifting, colliding, reforming. This cycle would continue for billions of years, shaping the surface of the planet in ways that would influence climate, ocean currents, and the evolution of life.
The land was still barren. No plants, no animals, no soil, just bare rock, weathered by wind and rain. But the stage was being set. The pieces were moving into place. And deep in the ocean, life was preparing for its next great leap.
The Proterozoic Eon, from the Greek meaning earlier life, a time when life was still simple but beginning to change. The great oxidation event had passed. Oxygen was now a permanent part of the atmosphere, though still far lower than today's levels. And the continents were moving. Around 2.1 to 1.8 billion years ago, they began to merge into a supercontinent. Not the first, perhaps, but the first we have solid evidence for. It's called Columbia, or sometimes Nuna. Columbia was massive. Not as large as Pangaea, which would come much later, but still enormous. It stretched from what would become North America to Australia, all fused together into a single landmass. The interior of Columbia was dry. Rain fell on the coasts, but by the time weather systems reached the center, they had lost most of their moisture. The heart of the supercontinent may have been a vast desert. The ocean that surrounded Columbia was called Merovia, a single global sea unbroken by land.
Life in this ocean was still simple. Single-celled organisms dominated. But something new was beginning to appear. Eukaryotes, cells with a nucleus. Unlike bacteria, which have their genetic material floating freely in the cell, eukaryotes keep their DNA inside a membrane-bound nucleus. This structure allows for more complex organization and regulation. The first eukaryotes likely evolved around 2 billion years ago, possibly earlier. They may have arisen when one cell engulfed another, and instead of digesting it, kept it as a symbiotic partner.
This process, called endosymbiosis, gave rise to mitochondria, the organelles that power eukaryotic cells. Later, some eukaryotes would engulf photosynthetic bacteria, creating chloroplasts and giving rise to algae and eventually plants. But for now, eukaryotes were just another type of microbe, drifting in the ocean alongside their bacterial cousins. Columbia remained stable for hundreds of millions of years. But supercontinents do not last forever. Around 1.5 billion years ago, it began to break apart. Rifts opened. New oceans formed between the fragments. The pieces drifted away from each other, scattering across the globe. And once again, the continents were on the move.
For billions of years, Earth had been warm. Even with a dimmer sun, greenhouse gases in the atmosphere kept temperatures moderate. But things were changing. Around 850 million years ago, the climate began to shift. Temperatures dropped. Ice formed at the poles, spreading outward. At first, it was just polar ice caps, similar to what Earth has today. But the ice didn't stop there. It kept spreading.
The more ice that formed, the more sunlight was reflected back into space. This created a feedback loop. Less heat absorbed meant more ice. More ice meant less heat. The planet was cooling rapidly. Within a relatively short period, geologically speaking, ice covered the entire planet. From pole to pole, Earth froze solid. This is called snowball Earth. It happened not once, but at least twice. The first around 850 million years ago. The second around 635 million years ago. During these events, the oceans froze to a depth of over a kilometer in some places. The entire surface was covered in ice and snow, reflecting nearly all incoming sunlight back into space. Temperatures plummeted, possibly as low as minus 50 degrees Celsius.
Life, which had been thriving in the oceans, suddenly found itself trapped beneath a thick layer of ice. But life is resilient. Near hydrothermal vents, deep in the ocean, where heat still rose from the mantle, ecosystems persisted. Microbes clustered around these vents, feeding on chemicals rather than sunlight. And even in the frozen surface waters, some organisms survived, lying dormant, waiting for the ice to melt. So how did Earth escape from snowball conditions? Volcanoes. Even with the surface frozen, volcanic activity continued. Carbon dioxide from eruptions accumulated in the atmosphere. With the oceans frozen, there was nothing to absorb it. Over millions of years, CO2 levels rose, the greenhouse effect intensified, and eventually the temperature climbed high enough for the ice to begin melting.
Once it started, the process accelerated. Less ice meant more heat absorption. More heat meant more melting. Within perhaps a few thousand years, Earth went from completely frozen to completely thawed. The transition was dramatic. The climate swung from ice house to hothouse in the blink of an eye, geologically speaking. And when the ice melted, life exploded. The snowball Earth events may have been one of the most important drivers of evolution in Earth's history. The extreme conditions forced organisms to adapt, to find new strategies for survival. And when the ice retreated, those survivors found a world rich in nutrients, ready to be colonized. The stage was set for complexity. After the ice melted, something changed. For billions of years, life had been microscopic.
invisible to the naked eye. But around 635 million years ago, the first large, complex organisms appeared. They are called the Ediacaran biota, named after the Ediacara Hills in Australia, where their fossils were first discovered. These creatures were unlike anything that exists today. They were soft-bodied, with no shells, no bones, no hard parts at all. Most were flat, often frond-like, resembling plants more than animals. Some looked like quilted mattresses, segmented bodies lying on the seafloor. Others were disc-shaped or tubular or branching like ferns.
They lived in shallow seas, often anchored to the ocean floor, filtering nutrients from the water or possibly photosynthesizing with the help of symbiotic algae. There were no predators yet, no teeth, no claws, no eyes, just soft, strange forms living peacefully in a world without violence. This was the Ediacaran Garden, a strange, serene period in Earth's history when life was large but not yet dangerous. Some scientists believe the Ediacaran organisms represent an entirely separate experiment in multicellular life, one that ultimately failed when the Cambrian explosion brought more competitive, more predatory forms.
Others think they are the ancestors of modern animal groups, early experiments in body plans that would later be refined. The truth is, we don't know. Their fossils are rare, often ambiguous, and their relationship to modern life is one of paleontology's great mysteries. What we do know is that they existed. They were large, they were complex, and they filled the oceans for nearly 100 million years. But their time was ending. Around 541 million years ago, the Ediacaran biota began to disappear. Whether they were outcompeted, eaten, or simply displaced by a changing environment, we're not sure. What is certain is that a new era was beginning, one filled with shells, teeth, and eyes. One where survival required more than just existing. It required strategy. The Cambrian was coming.
Oxygen levels had been rising slowly for over 1 billion years. After the Great Oxidation Event, oxygen made up perhaps 1% of the atmosphere. Not much, but enough to change the chemistry of the planet. Over time, as photosynthetic organisms continued to thrive, oxygen levels climbed. By the end of the Proterozoic, around 541 million years ago, oxygen made up about 10 to 15% of the atmosphere, still lower than today's 21%, but high enough to support larger, more active life. This rise in oxygen is one of the key factors that allowed complex life to evolve. Single-celled organisms can survive on very little oxygen, but larger organisms with more cells need more energy, and aerobic respiration, the process of using oxygen to break down food, provides far more energy than anaerobic processes. With higher oxygen levels, animals could grow larger, they could move faster, they could develop muscles, nervous systems, and sensory organs. But oxygen alone wasn't enough. The evolution of multicellularity required other innovations. Cells needed to communicate. They needed to specialize, taking on different roles within the organism. They needed to coordinate their actions. This required new genes, new regulatory systems, new ways of organizing life. Somewhere around 800 to 600 million years ago, these innovations came together. Multicellular life evolved, possibly multiple times in different lineages. The first animals were simple, just clusters of cells working together, but over time they became more organized. They developed tissues, layers of cells that performed specific functions. Some cells formed protective outer layers. Others formed digestive cavities. Still others became muscle or nerve cells. By the late Proterozoic, animals with true body plans had appeared. They had fronts and backs, tops and bottoms, left and right sides. They could move directionally. They could sense their environment. They could hunt or flee. And once predation appeared, evolution accelerated. Prey developed defenses, shells, spines, speed. Predators developed better tools for hunting, sharper teeth, stronger jaws, better vision. This arms race drove the explosion of diversity that was about to unfold. The Proterozoic was ending. For over 2 billion years, life had been simple, patient, waiting. Now, it was ready to explode. Anomalocaris, a predator over a meter long, hunted with grasping appendages and a circular mouth full of teeth. Hallucigenia, a bizarre creature with spines on its back and legs beneath, walked on the ocean floor like something from a dream. Opabenia, with 5 eyes and a trunk-like appendage, defied categorization. These were not the ancestors of modern animals. They were experiments, body plans that evolution was trying out, seeing what worked. Many of these designs failed. Entire groups went extinct, leaving no descendants. But others succeeded. The basic body plans that arose during the Cambrian, arthropods, mollusks, chordates, and echinoderms, are still with us today. Why did this explosion happen? There's no single answer. It was likely a combination of factors. Rising oxygen levels provided the energy needed for larger, more active bodies. The evolution of eyes created an arms race. Predators could see their prey. Prey evolved defenses. The feedback loop accelerated evolution. Genetic innovations like the Hox genes that control body patterning allowed for more complex body plans. And ecological opportunities opened up. With no established ecosystems, there were niches everywhere waiting to be filled. For 50 million years, the Cambrian seas were a riot of experimentation. Strange forms, bizarre adaptations, a level of diversity that has never been matched. The first forests appeared around 385 million years ago, but they were unlike any forest today. The trees were not oaks or pines. They were giant ferns, club mosses, and horsetails, some reaching heights of 30 meters. The forest floor was covered in decaying plant matter. Fungi broke it down, recycling nutrients back into the soil. Millipedes and other early arthropods crawled through the undergrowth. And then, animals followed. The first creatures to leave the water were likely arthropods, scorpion-like animals venturing onto land to escape predators or find new food sources. But the most significant transition was yet to come. Around 375 million years ago, a group of fish began to explore the shallows. They had lobed fins, fleshy appendages with bones inside, similar to the limbs of land animals. These fish, called lobe-finned fish, could use their fins to push themselves along the muddy bottom. Some could even breathe air, gulping it at the surface when oxygen levels in the water were low. One group of these fish, the tetrapodomorphs, began spending more time on land. Their fins evolved into limbs. Their bodies adapted to support weight outside of water. Their lungs became more efficient. By 365 million years ago, the first true tetrapods had evolved, 4-legged vertebrates capable of walking on land. They were still tied to the water. They laid their eggs there. They hunted there. But they could survive on land, breathing air, exploring a world no vertebrate had ever seen. The conquest of land had begun, and it would change everything. The continents were moving again. After millions of years of drifting separately, they began to collide. Around 320 million years ago, the supercontinent of Pangaea started to form. Pangaea, from the Greek meaning all Earth, the largest supercontinent in Earth's history. It stretched from pole to pole, a single massive landmass surrounded by a single ocean, Panthalassa. The interior of Pangaea was harsh. Far from any ocean, the climate was extreme, scorching hot in the summer, freezing in the winter. Rainfall was rare. Much of the interior was desert. But along the coasts and in the equatorial regions, life thrived. The Carboniferous period, from 360 to 300 million years ago, was the age of giant insects, with oxygen levels at their highest in Earth's history, possibly as high as 35%. Arthropods grew to enormous sizes. Dragonflies with wingspans of 70 centimeters, millipedes over 2 meters long, scorpions the size of house cats.
The forests of this time were vast. Swamps covered much of the land, filled with towering trees that would eventually become the coal deposits we mine today. Amphibians ruled these swamps. Massive, crocodile-like predators, some over 4 meters long. But a new group was rising. Reptiles. Animals that had evolved a crucial adaptation, the amniotic egg. Unlike amphibians, which had to lay their eggs in water, reptiles could lay eggs on land. The eggs had a protective shell and internal membranes that kept the embryo moist and safe. This freed reptiles from dependence on water. They could venture deep into the interior of Pangaea, colonizing environments no amphibian could reach. By the late Permian, around 260 million years ago, reptiles dominated the land. Some were herbivores, feeding on the abundant plant life. Others were predators, hunting in packs or ambushing from cover. One group, the synapsids, would eventually give rise to mammals, but that was still far in the future. For now, Pangaea was a world of reptiles, vast, diverse, thriving. But it would not last. 252 million years ago, something went catastrophically wrong. It started in what is now Siberia. Massive volcanic eruptions, unlike anything seen before or since, began spewing lava across the landscape. These were not ordinary volcanoes, they were flood basalts, fissures in the crust that released unimaginable quantities of molten rock. For 1 million years, lava flowed, covering an area the size of Europe. But the lava was not the worst part. The eruptions released massive amounts of carbon dioxide and sulfur dioxide into the atmosphere. The sulfur caused acid rain, the CO2 triggered runaway global warming. Temperatures soared, the oceans warmed, oxygen levels in the water plummeted, vast dead zones formed. On land, the heat was unbearable. Forests burned, rivers dried up, entire ecosystems collapsed. And then, the methane hydrates released. Frozen methane stored in the ocean floor began to thaw as the water warmed. Methane, a greenhouse gas far more potent than CO2, bubbled to the surface and entered the atmosphere. This triggered even more warming, a feedback loop that accelerated the crisis. Over the course of perhaps 60,000 years, 90% of all species on Earth went extinct. This is called the Permian-Triassic extinction, the Great Dying, the most severe mass extinction in Earth's history. Marine ecosystems were devastated. Trilobites, which had survived for 270 million years, vanished entirely. Reefs collapsed. The oceans became nearly lifeless. On land, the synapsids, which had dominated for tens of millions of years, were nearly wiped out. Only a handful of species survived. For millions of years afterward, Earth was a wasteland. Recovery was slow. Ecosystems were simplified, dominated by a few resilient species. But life, as always, found a way. And from the ashes of the Permian, a new group would rise. The dinosaurs were coming.
The Triassic period began in the aftermath of extinction. The world was hot, dry, and mostly empty, but slowly life returned. Among the survivors were a group of reptiles called archosaurs. They were small, mostly bipedal, with long legs built for running. One branch of archosaurs would become the crocodilians. Another would become the pterosaurs, the first vertebrates to achieve powered flight. And a third branch became the dinosaurs. The first dinosaurs were small, no larger than a dog. They appeared around 230 million years ago, during the Middle Triassic. For millions of years, they were not dominant. They coexisted with other reptile groups, competing for resources. But then, another extinction event occurred. At the end of the Triassic, 201 million years ago, massive volcanic eruptions triggered a mass die-off. Many of the dinosaurs' competitors vanished. The dinosaurs survived. And in the Jurassic period that followed, they diversified rapidly. Some became herbivores, massive long-necked sauropods like Brachiosaurus and Diplodocus, some weighing over 70 tons. They fed on the tops of trees, reaching heights no other animal could. Others became predators. Theropods like Allosaurus, with powerful jaws and sharp claws, hunted in packs or alone. And some took to the air. Though birds would not evolve until later, small feathered dinosaurs were already experimenting with gliding and powered flight. By the Cretaceous period, 145 to 66 million years ago, dinosaurs ruled every continent. They adapted to forests, deserts, swamps, and coastlines. Tyrannosaurus rex, one of the largest land predators ever, stalked the forests of North America. Triceratops, with its massive horns and frill, roamed in herds. Pterosaurs, with wingspans of 10 meters, soared over the oceans. The world was warm. Sea levels were high. Flowering plants had recently evolved, bringing color and new food sources to the landscape. For over 160 million years, dinosaurs dominated. They were the most successful large animals in Earth's history. But their reign was about to end. 66 million years ago, on an ordinary day in the late Cretaceous, the sky caught fire. An asteroid roughly 10 kilometers across entered Earth's atmosphere traveling at 20 kilometers per second. It struck the Yucatan Peninsula in what is now Mexico, creating a crater 180 kilometers wide. The impact released energy equivalent to billions of nuclear bombs. The ground vaporized instantly. A shockwave rippled outward at supersonic speed, flattening everything for hundreds of kilometers. Molten rock was flung into the atmosphere, raining back down across the planet, igniting wildfires on every continent. The impact triggered massive earthquakes. Tsunamis hundreds of meters high swept across the oceans. But the worst was yet to come. Dust and soot filled the atmosphere, blocking out the sun. Temperatures plummeted. Photosynthesis stopped. Plants died. Herbivores starved. Predators followed. This impact winter lasted for years, possibly decades. 75% of all species on Earth went extinct. The non-avian dinosaurs, which had ruled for over 160 million years, vanished entirely. Pterosaurs disappeared. Marine reptiles like mosasaurs and plesiosaurs died out. But some life survived. Small mammals, which had lived in the shadow of dinosaurs for millions of years, endured. They were small, adaptable, able to survive on limited food. Birds, the descendants of small theropod dinosaurs, also survived. Their ability to fly allowed them to find food and escape danger. Crocodiles, turtles, and some lizards made it through. deep-sea creatures, insulated from the chaos above, were largely unaffected. When the dust finally settled, the world was unrecognizable. The age of dinosaurs was over. A new age was beginning. With the dinosaurs gone, mammals filled the void. They had existed for over 160 million years, but always as small, nocturnal creatures, hiding from the giants that ruled the day. Now, for the first time, they could emerge. They could grow larger. They could explore niches that had been closed to them. Within 10 million years, mammals had diversified into dozens of new forms. Some became herbivores, feeding on the recovering plant life. Others became predators. Still others took to the trees, the water, or the air. Primates evolved around 55 million years ago. Early primates were small, tree-dwelling creatures with grasping hands and forward-facing eyes. Whales evolved from land-dwelling mammals that returned to the sea. Over millions of years, their legs became flippers, their bodies streamlined. Bats evolved the ability to fly, the only mammals to do so. And on the plains of Africa, around 7 million years ago, a group of primates began walking upright. These were the hominins, the ancestors of humans. They were not yet intelligent, not yet tool users, but they had taken the first step. For millions of years, the world was warm. Forests covered much of the land. The poles were ice-free. The climate was stable. But that was about to change.
Around 2.6 million years ago, the climate began to cool. Ice sheets formed at the poles, spreading outward. Glaciers advanced across the continents. The Pleistocene epoch, the age of ice, had begun. The ice did not come all at once. It advanced and retreated in cycles, driven by changes in Earth's orbit and tilt. During glacial periods, ice covered much of North America, Europe, and Asia. Sea levels dropped as water was locked up in glaciers. Land bridges appeared, connecting continents that had been separated for millions of years. During interglacial periods, the ice retreated, temperatures warmed, forests returned. But then, inevitably, the ice came back. These cycles repeated dozens of times over 2.5 million years. The ice shaped the landscape. Glaciers carved valleys, lakes, and fjords. They deposited sediment, creating hills and plains. And life adapted.
Woolly mammoths, giant sloths, saber-toothed cats, massive creatures built to survive the cold. And humans. Our ancestors evolved during this time. They learned to make tools, control fire, hunt in groups. They migrated out of Africa, spreading across the globe. By 11,700 years ago, the last ice age was ending. The glaciers retreated for the final time. The climate warmed. And humans, no longer just survivors, began to build civilizations. The age of ice was over. The age of humanity had begun. And here we are, 4.5 billion years after a cloud of dust began to collapse. 4 billion years after the first oceans formed. 3.5 billion years after life appeared. Right now, you are resting on a planet that has been frozen solid, melted entirely, bombarded by asteroids, and reshaped by continents colliding. Beneath your feet, the core of the Earth still spins, generating the magnetic field that shields you from solar radiation. Above you, an atmosphere rich in oxygen, created by billions of years of photosynthesis, sustains your every breath. And around you, life in all its forms, from bacteria in the soil, to trees in the forest, to the thoughts in your own mind, continues the process that began so long ago. This planet has been through so much. It has survived. It has adapted. It has changed in ways we can barely comprehend. And yet, here it is, turning quietly in space, hosting life, creating beauty. The story is not over. Earth will continue to change. Continents will drift. Climate will shift. Species will evolve and go extinct. But for now, in this moment, you are part of it, a tiny thread in the vast tapestry of deep time. And perhaps that's enough, to know that you are connected to something ancient, something vast, something that has endured for longer than we can truly imagine. Sleep well. The earth will keep turning, and when you wake, the story will still be unfolding. Thank you for spending this moment with me. If this journey brought you peace, consider liking, subscribing, and sharing it with others who might need it. Good night, and rest easy, knowing you are part of something far greater than yourself.